on pretty much chapter 6, which was balancing equations and stuff like that. I know in lab, I think as well, you went through that, I hope. And also, I think for us, we also had that little last part of 8 I put up there as well. I think between the two, it was less than an hour, I think, of lecturing. So make sure you do watch that. But just to, again, reiterate, in terms of balancing equations, when we do balance equations, it is only the coefficients that we change. So if we had something like N2 plus H2 gives us NH3. The idea of balancing equations, which you should always make sure that obviously you do have an equation that is balanced, is to make sure that you have the same number of elements on each side. And that's because, again, in a chemical reaction, the only thing that's really happening is we're breaking bonds and making new bonds. So it's all about the electrons. We don't do anything with the protons or neutrons, which are in the nucleus. And that means that we do have, obviously, the conservation of each element. So if we start with a certain amount of elements on one side, we should also end with the same amount of elements on the other side. There's a couple different ways you can balance equations, but sometimes it's helpful to make a little table just to sort of see how much of each thing you got. So on the left-hand side there, we have 2. Right-hand side, we have 1 nitrogen. Left-hand side, we have 2 hydrogen and 3 hydrogens on the right-hand side. It sometimes gives you a good place to sort of start with. Personally, for me, I go with what seems like the easiest to balance first. So that's, to me, seems easiest. I save anything where there's kind of multiples of the same element in different sort of compounds on one side and the element by itself on the other side for kind of the end. So in this case, I would start with the nitrogen, which would put a 2 here. That gives us 2 nitrogens. And again, that 2 does go for that guy there. So that does give us 6 hydrogens. We can now see that the nitrogen is balanced. We could go to the hydrogens and add a 3 in front of it. And that again would give us 2 and, if I could do math, 6 hydrogens there on the left, and it would be balanced in this case. A reminder, right, the left-hand side of the arrow are our reactants, right, which are our starting material. Thank you. And on the right-hand side, there are our products, which is the stuff that is produced as a result of a chemical reaction. Now, just do a couple here just to make sure. So what we do, let's do C3H8 plus O2 gives you CO2 plus some water. And we have 1. Left-hand side, we have 8 hydrogens, and right-hand side, we have 2. Left-hand side, we have 2 oxygens, and again, here we do have 3 oxygens on the right-hand side in each of those things. Once again, here, I'm going to start with what seems easy, and that seems like the carbon would be easy. So I'm going to put a 3 in front of my CO2. That's going to give me 3 carbons. That will give me still 2 hydrogens. And for oxygen, that's going to be 6 there, plus 1 more over here, which would give me 7 in this case. At this point, the next easiest thing really to balance is the hydrogen. I'm not going to go for the oxygen because it's in multiple places on the right-hand side and kind of by itself on the left. But hydrogen is just in one place on each side. So that makes it much easier to sort of fix. So we'll put a 4 there in front of it. That gives us 3 carbons. 4 times 2 is 8 hydrogens. And in terms of oxygen, that again is 6. And now we need to multiply the 4 over, which gives us 10. At this point, we could go to the left-hand side and put a 5 in front of the oxygen to fix it. Gives us 3, 8, and 5 times 2 is 10. Any question on that one there? Now, for the second one, you could definitely go element by element, but in this particular case, we do have a number of polyatomic ions present. We got sulfate and sulfate. We have hydroxide and hydroxide. So a lot of times when you're balancing an equation that has polyatomic ions in it, you, like I said, can't go element by element, but there's probably a greater room for error as you got to kind of multiply in, multiply out, and kind of keep track of everything. Sometimes it's a lot easier just to balance them as kind of like units of polyatomic ions and start with there. So for me, I would look at, say, the sulfate here, and I got 1 sulfate there. And on this side, I have 3. So to fix that, I could just put a 3 in front of it. When I do that, that gives me 3 of the sulfates. And it also, in this sort of method, tells you where you should go next, which is also the iron gets changed by putting that 3 in front of it. So that gives me 3 irons on the left, only 1 on the right, which means I need to put a 3 to the iron on the right-hand side. That gives me 3 irons. That also then changes the hydroxide from 2 to 6. And that is where I should go next. So I go back to the left-hand side, and to fix the hydroxide, I just need to put a 2. That also takes care of the aluminum as well. And that usually is what happens. Everything kind of falls into place as you kind of do that. So it's sometimes a lot faster and a lot easier when you have equations that do have polyatomic ions in it on each side, to just kind of balance those guys first and keep them together, and everything sort of falls into place a lot easier. Any questions on any of that? Last reminder here again about balancing. We obviously can use fractions, right, to balance something, but we do need to get rid of the fractions when it's all said and done. Yeah, so talked about fractions balancing. If not in our video, we did. So you do need to make sure you get rid of a fraction. So when you have a properly balanced equation, when it is all said and done, let's just say that this was properly balanced. Although it may be balanced, you could go through the coefficients here and reduce it down by, say, 2 and still get whole numbers. And you should do that. So, you know, sometimes it does happen. People see maybe the bigger numbers, and it is definitely balanced. But if you could go through all the coefficients and reduce them all down by a common number and still have whole numbers, then that would be the proper way to balance that equation. You should take it down to the simplest set of whole numbers. Any questions on any of that there? Okay, so then we're going to go into chapter 7, really, which is what this is. And we're going to talk about really different ways that you could classify reactions and some different types of reactions. Pretty much all reactions boil down to kind of 3 things as to why it took place. So there's really kind of 3 driving forces for reactions. Basically 3 reasons why it takes place. The first reason is the formation of a solid, sometimes referred to as a precipitate, which is a PPT abbreviation. The second reason why really a reaction took place was the formation of water. And the third reason why a reaction takes place is basically an electron transfer. So pretty much all reactions that you come across that are chemical reactions, pretty much one of these 3 things are happening. And that's really why the reaction is taking place. Either you make a solid, either you make water, or you have some type of electrons being transferred as the result of the process. With that being said, pretty much of reactions basically fall under 2 umbrellas, basically. So the one umbrella is double displacement reactions. And in a double displacement reaction, it has a general form of AB plus CD. And what each of these guys are actually ionic compounds. So you have 2 ionic compounds that are basically there. And what happens in a double displacement reaction is the 2 positive guys basically switch partners. So the 2 positive guys will basically do a switcheroo there. And you'll form 2 new ionic compounds on the other side. You will form A and D, for example, plus C and B. Now, in in cases, as a result of these guys basically switching partners, one of those guys on the product side will make a solid. So perhaps one of these guys make a solid. And that takes care of the first reason why a reaction takes place, the formation of a precipitate. In other cases, more specifically, usually when an acid and base comes together, one of those guys on the right-hand side basically makes water. So it basically becomes water on the other side. So maybe this guy ends up being water, which is really the second reason a reaction will take place, formation of water. So the really big sort of classification of reactions is double displacement reactions. As we will see underneath that classification, you can more specifically classify a reaction as either like a precipitation reaction, an acid-base reaction. So they fall under there. Pretty much every other reaction falls under the topic of redox reactions. And redox reactions basically takes care of the third reason why a reaction takes place. It takes care of a transfer of electrons basically happening. So in terms of sort of big classifications, those are the two really big categories of reactions. Underneath each of these categories are, again, a more specific way you can classify reactions, like synthesis, like combination, like decomposition. They fall under one of these sort of two categories. As we will see in this chapter and talk a little bit more about, you could take one reaction, and depending on what you're looking at, you could classify that one reaction in like 3 different ways. You could call it basically 3 different types of reactions, depending on sort of what you're looking at. So the first thing we're going to look at, though, is reactions in aqueous solutions. Aqueous solutions are the guys that basically have the AQ sort of symbol next to it. It's basically a water environment is basically what aqueous is. So let's take a look at some of this here. So an aqueous solution, pretty much all biologicals and a lot of chemical sort of reactions take place in an aqueous environment. And a solution is actually a homogeneous mixture of 2 or more substances together. Homogeneous, if you remember, means everything mixes, everything looks the same throughout. It just looks like one thing. And there's really 2 parts to a solution. There is the solute, which is the smaller part. And there is the solvent, which is the larger part of a solution. So aqueous, guys, is different than something that has just the liquid designation to it. Aqueous means this type of situation is occurring. So for example, if we took some water, which is a pure liquid, and we reacted or added to it some solid sodium chloride, these 2 guys would dissolve in each other. So the sodium chloride would dissolve in the water, and you would be left with sodium chloride solution that gets the aqueous sort of symbol next to it. In this example here, the solute is the sodium chloride. So the solute here would be the sodium chloride. And the solvent would be water. So when you take both of those things together, you get a solution. Water is a really good solvent for things that are ionic, for things that are polar, because they're able to interact with each other really well. They interact with each other basically through positive negative attraction. So something like water, which is polar, has a negative side and a positive side, right, where the hydrogens are. And it allows it to interact well with ionic compounds and also other things that are polar as well. How do you know what the solute is? It's a pretty easy answer. Whatever the name of the solution is the solute. So you have a sodium chloride solution, sodium chloride was like dissolved in water. If you have a calcium chloride solution, calcium chloride would be the solute. Again, in most cases, if it's an ionic sort of solution or compound, Probably water's the solvent. Water doesn't always have to be the solvent, and in certain cases, it's a really crappy solvent. But a lot of times, water is oftentimes a solvent. For example, if you had something that was nonpolar, water would be a really terrible solvent for it. It has no way to interact with it. So if you remember, maybe back when they did the halogen experiment where you had the different layers, right? And the colors changed from the top layer to the bottom layer and all that kind of stuff. The bottom layer was the water layer, and the top layer was the heptane, I think you guys used. And that's organic, which is nonpolar. And that's basically what happens when you have water and something that's nonpolar come together. They basically separate out because they have no way to interact really well. So you get the different layering. They really don't mix or anything like that. So because they really don't mix, they can't make a solution, because a solution is something that's homogeneous, which means that it mixes together really well. So let's talk a little bit about electrolytes. Electrolytes are substances that, when they do go for a swim, if you will, they will produce ions. So electrolytes are really guys that can conduct electricity, and really the reason they can conduct electricity is they produce ions. So the presence of these ions, these positive and negative ions in solution, helps kind of complete the circuit, if you will, and helps electricity be conducted. Now, a non-electrolyte is something that will dissolve in, say, something like water, but it will not produce any ions. And because it doesn't produce any ions, basically it will not be able to conduct electricity. So for example, if you took something like sugar and you dissolved it in water, we know that sugar will dissolve in water, but sugar is carbon, hydrogen, and oxygen. Those guys are covalently bonded, sharing of electrons, which means they're not going to produce any ions. So because they don't produce any ions, they will not conduct electricity. Now, some strong electrolytes are pretty much ionic compounds. So it's almost a safe bet if it's an ionic compound, it's going to be a strong electrolyte, which means obviously if we took something like sodium chloride in solution, it will 100% break apart into sodium ions and chloride ions. So in the actual solution, you would have none of the sodium chloride units still together. So if I do an award-winning drawing of a beaker and you had that, you basically would just have these ions floating around, chloride ions, but you would have none of the sodium and chloride still together in that solution. And that's why it's a really strong electrolyte, because you basically just produce a lot of ions really quickly. It's going to be able to conduct electricity really, really well. At a lot of schools and stuff, they would do an experiment where they take a light bulb, and again, they would hook some electrodes to it and stick it into a solution like this. And if they did, the light bulb would go off very, very brightly. So it would conduct electricity really, really well. It would go off very, very bright because you have all those ions that are in that solution helping it conduct electricity. In addition to ionic compounds such as that, I guess sort of still ionic compounds, strong acids and strong bases are also strong electrolytes. So anything that is like a strong acid or a strong base are also strong electrolytes. So for example, hydrochloric acid, which is a strong acid, will in solution 100% break apart into H plus and Cl minus ions. So 100% in solution, that's what you have. That's also why it's considered a strong acid. An acid is something that can produce H plus. So when something like hydrochloric acid goes for a swim, in addition to being a strong electrolyte, it basically produces a lot of H plus really, really quickly, which is why it is a strong acid, which is a strong electrolyte. Something like sodium hydroxide is a strong base. And same thing in solution, you have none of the sodium hydroxide units together. You have basically 100% what's on this side in the solution. And that's also why it is a strong base, because the definition of base is something that could produce OH minus, and it obviously would produce a lot of OH minus really quick.
Compounds not electrolytes, or not all compounds?
So for the most part, covalent or molecular compounds will probably fall under the non-electrolyte sort of banner. Again, because they're sharing electrons, even when they go for a swim, if they're able to dissolve, they won't produce any ions. Now, remember that something like an acid, which really is sort of non-metal, right? Hydrogen is a little bit different. It almost is like a sort of like an ionic compound. So that's why when something like HCl, which technically is two non-metals together, and technically speaking, still sharing electrons, it's able to, for other reasons outside this class, actually produce the H plus ion in solution. So I would say outside of like an acid or a base or really an acid situation, probably if it's molecular, it probably would fall more on the non-electrolytes because it won't produce ions. Other questions? Now, very effective solvent for a lot of ionic compounds and also polar compounds, really because it is a polar molecule. And pretty much it's able to, as I mentioned, because there's a negative side and a positive side to water, it's able to really interact well when you take something like a strong electrolyte like sodium chloride and you dump it into solution or into water. Basically what happens is it breaks apart into its ions, the sodium and the chloride, for example. And what helps it dissolve and actually sort of go away visually from us is the attraction to the water molecules, because there's so many water molecules in there where you dump the sodium chloride. The negative side of water will actually be attracted to the positive ion, which is the oxygen side. On the same token, the positive side of water, which is the hydrogen side, will be attracted to the negative ion that's there. And that's really how something dissolves. It sort of disappears, right? We no longer can see it. Is because there's a heck of a lot of water molecules just basically just surrounded them all, and visually we cannot see it. We know it's still there because you've done some experiments where you had some solution at the end, you put your evaporating dish up there, right? And you evaporated off the water part, and what you were left with was a solid that reappeared, right? And that is, again, we got rid of all the water out of the way, so we could then have the positive and negative ion come back together because they're very much attracted to one another. The sort of hydration of this also serves a purpose to keep those ions apart from one another, because if the water wasn't there, they definitely would be strongly attracted to one another. So it kind of serves two purposes of it. We help things dissolve by mixing, right? So when you mix, you're just throwing a bunch of water molecules all over the solid, and it helps the process to get those water molecules surrounding each of those ions. Also provides some energy as you do it, right? That helps it sort of dissolve. Water is also a really good solvent for something that is polar. So if you have a polar molecule, what that means is overall, there is a positive side to the molecule and a negative side to the molecule. And that positive side, for example, of the polar molecule would be attracted to the oxygen side, and that allows water and that polar molecule basically to interact. Pretty much how most molecules interact with other molecules is really just the basic interaction of positive, negative attraction. So that's the basic interaction of how things dissolve in each other, how things mix with each other is, oh, you got a positive side, I have a negative side, I'm attracted to you. Or in the case, if you took something like water and you try to do something with a nonpolar molecule, a nonpolar molecule basically is sharing electrons equally, which basically means that this molecule is neutral. There is no positive side, there is no negative side. So when that guy and water gets together, water is looking to do some type of positive negative attraction. The non-polar guy is like, I can't really help you out with that very much. It doesn't really have a way to do it. It is able to temporarily get itself to a positive negative state, but it can't hold it. So that's why those interactions don't really last very well. So if you think something like oil, which is non-polar, and water, right? Oil eventually gets to the top, right? Same thing with the halogen experiment we were just talking about, right? The bottom part of that test tube was the water layer. Top part was the organic non-polar guy. So they separate out from each other like oil and vinegar salad dressing, right? You can mix it for a while, right? Stays mixed, but if you let it sit, eventually everything sort of separates out. And that's because over the long period of time, something that's non-polar and something that's polar has no way to maintain that interaction. As opposed to when a water and a polar molecule gets together, the polar molecule, no matter what happens, always has a positive negative side. So it's good to go. They're able to maintain that interaction and interact really well with each other. So that's why water is a very good solvent for ionic things. Polar things, a terrible solvent for something that is non-polar. Any questions on that there? So that process where water really surrounds all the ions as it goes into solution is sometimes referred to as the process of hydration. And as I mentioned, the water serves really two purposes. It allows it to dissolve, and it really does keep those opposite charged ions away from one another to prevent them from coming together. So as we talked about before, acids are also electrolytes, and some strong acids like HCl, HNO3. Let's add to our lists here. H2SO4 is a strong acid. Perchloric acid is a strong acid. HBr is a strong acid. HI is a strong acid, along with the other two that are up there, HCl and HNO3. These are all strong acids, which means they are all strong electrolytes, and they will 100% break apart in solution. Now, if you need to decide, is that a strong acid or not a strong acid, that's a good list to always remember if you plan on continuing through chemistry. Pretty safe bet that if it is not one of those guys, it's probably going to be more of a weak acid. So that's a really good list to kind of keep in mind as you go through classes, especially 1B when you get there and you talk a lot about acids and bases. Now, weak acids are like some weak electrolytes. So weak acids like HF, this is acetic acid here, which is sometimes abbreviated as C2H4O2. Nitrous acid, carbonic acid, HCN, also some weak acids. Now, weak acids are weak electrolytes, and there is a difference between a strong electrolyte and a weak electrolyte. A weak electrolyte will mainly stay together, but will produce some ions. So unlike a strong electrolyte, which is pretty much a one-way street, everybody's dropping out into solution as ions. In a weak electrolyte, it's actually going to mainly stay together, but it will break apart a little bit and produce a little bit of ions. So for example, the one on the bottom there are HF, which is hydrofluoric acid, is a weak electrolyte. It will break apart a little bit into H plus and F minus. So you'll produce a little of these guys, but it will mainly stay together. And basically, if you drew a picture of what's going on with that in solution, you mainly have this guy all together, but you'll have a little bit of the ions basically breaking apart. So because of that, a couple of things, it is still an electrolyte because it's able to produce a little bit of ions, which means if we kind of take that light bulb example that we talked about earlier, if you stuck that electrodes from that light bulb in there, the light bulb would turn on, but it would be very dim. so it wouldn't be conducting electricity a lot, but it would still be able to conduct electricity. So if you kind of stuck that light bulb in there, it would come on, but it would be dim. The other thing that you could kind of use to help you to see that it is a weak electrolyte is these reversible arrows. And these reversible arrows indicate that the reaction goes in two directions. It goes from reactants to products, which is the forward direction, reactants to products. And at some point, you'll build up enough products that they will combine and go the opposite way, which is what is referred to as the reverse direction. So in a weak electrolyte, you basically have the reaction going in both directions. You'll build up some products. Once products get built up, they'll come back the other way and make some reactants. So that is a main difference between that and a strong electrolyte. Weak acids, like I listed there on the right, are weak electrolytes. They mainly stay together, but still are able to break apart a little bit. There are also some weak bases that does that as well. Probably the most common weak base that you come across a lot is NH3, which is ammonia. So ammonia is a weak base. Mainly will stay together, but can produce a little bit of ions along the way. So strong acids or strong electrolytes 100% break apart. Strong bases, which is pretty much most guys on group 1 or group 2 with hydroxide. So like sodium hydroxide, potassium hydroxide, hang right there to calcium hydroxide, strontium hydroxide, barium hydroxide. So all those guys that you put hydroxide on in group 1 and group 2 are strong bases, majority of them, and they are also strong electrolytes. So they 100% break apart into ions, again, producing that hydroxide, which is basically what makes them a strong base. Any questions on that there? So let's first talk then about precipitation reactions. So precipitation reactions, as I mentioned, basically is some type of solid gets formed. And once again, this is under the umbrella of double displacement reactions. So as we talked about before, that is our two ionic compounds, which will switch partners. And again, one of these guys will basically make a solid in this case. So sort of the big classification is double displacement. A more specific classification of that type of reaction is a precipitation reaction, which means some type of solid is formed. By the way, when you do a precipitation reaction, it doesn't have to make like a rock hard solid. It could just be some cloudiness that occurs, something mushy that wasn't there before, kind of floating around. So sometimes people think it's got to be like a rock hard solid, like drops to the bottom. It doesn't. So if it gets cloudy like that, that's really a solid that's being formed. And if you centrifuge that test tube that had that cloudiness, all that solid would compact to the bottom, and you'd be able to kind of see the solid a little bit better. So precipitation reactions are characterized by a precipitate that forms, and basically it's a result from a combination of two ions to come together. So there are some rules we'll talk about here that when two ions come together, sometimes when they come together, they make a solid, and other times they really don't come together. They don't mix and don't make any type of solid. And a precipitate is formed, and once again, shorthand that you see a lot for a precipitate is PPT. Is sort of the shorthand that means a precipitate. So if we look at this reaction here, we take a little lead to nitrate and a little sodium iodide. And I think are your notes, I'm not sure if it's correct or not, but there should be a 2 right about there. This is a certain type of equation which describes what is going on here. And this is the molecular equation, right? So what we see here is our molecular equation. And in a molecular equation, we pretty much write everybody out in their proper sort of chemical formulas, balancing everything. But basically what happens when we mix together, in this case, the lead 2 nitrate and the sodium iodide together, say in a beaker, when we kind of dump those guys into the beaker together, what is really happening is not really reflected there in this type of equation. So we can write another equation which sort of describes what's happening when we mix everybody together. And really, when we mix everybody together, anything that is a strong electrolyte, as we talked about, will pretty much break apart into ions when it's in solution. Anything that's a weak electrolyte will stay together. Anything that is a solid, a liquid, or occasionally a gas might pop in there. Those guys are also going to stay together because otherwise it wouldn't be a solid, right? If it broke apart. So it's got to be together to make that solid. So when we look at this equation, if we take it, what we really have going here is our lead with a 2+ charge coming from this guy. There are 2 of these nitrates, which means we actually have 2 nitrates floating around in that solution, which is why they get the aqueous symbol. For our sodium iodide, that 2 goes for both guys behind it. So we have 2 of these sodium ions that are floating around. We also have 2 of the iodide ions that are floating around. Coming to the other side, this guy is a solid. So once again, it needs to stay together to be a solid. So we would not break it apart. So that would give us our lead 2 iodide. And once again, this sodium nitrate is a strong electrolyte, which will break apart into a couple of sodium ions and a couple of nitrate ions here. So this equation really sort of describes what is truly happening when you take those 2 reactants basically and dump them together into the beaker. You got all this sort of happening here. This type of equation is what is referred to as a total ionic equation. Or sometimes people call it a complete ionic equation. Or people just sometimes just straight up call it an ionic equation. A couple of things about this equation. First off, there are ions present. When we write the formulas for ions, you should always include the charges. So if there are ions, you got to have the charges. Secondly, like I said, the things that we do not break apart, if it is a weak electrolyte, it stays together. You wouldn't break it apart into ions. If it is a solid or liquid, you also keep it together when you write this type of equation. When we get to this equation, it also allows us to see certain ions which are frankly not doing much. And we can recognize those by looking on both sides of the arrow. And when we look on both sides of the arrow, there should be some ions that look exactly the same. So for example, here, I got a couple of nitrates over here, and I got a couple of nitrates over on that side. I also have a couple of sodiums over here, and I got a couple of sodiums over here. They're the exact same ions on both sides of the arrow. Their exact numbers are the same. These guys are what are referred to as spectator ions. And if you are a spectator, you are doing what? You are watching, right? Hopefully, yeah. And that is basically what guys are doing. They're not really doing anything that is making the product of this reaction. They're just kind of there to balance out the charge. So they're just floating around in the solution, having a nice time. They're not really doing much. What we typically do with spectator ions in our total ionic equation is we treat the arrow like an equal sign and basically just cancel them out. You subtract it to both sides. And when we cancel out the spectator ions, what we are left with is really a third type of equation, which is really important. In this case, what is really going on is the lead 2 ion that comes from the lead 2 nitrate is going to find the iodide ion that comes from the sodium iodide. And those 2 guys are going to come together to make lead 2 iodide, which is a solid. And this equation is what is known as the net ionic equation. The net ionic equation pretty much cuts right to the heart of the matter and tells you when you mix those 2 things, this is what's happening. It's the lead finding the I, They're going to come together and make a solid. Good news here is they made a solid, which is one of the reasons why a reaction takes place, right? And this is why this is a precipitation reaction. What is really happening there is this yellow solid, which you'll make like in a week or so. Don't throw it in the trash can. They put signs everywhere. Don't put anything yellow in the trash can. This precipitate that's made is a precipitation reaction, and that is truly what is happening there. So these three types of equations are really important. The molecular equation, we write it just like normal. We use the entire sort of chemical formulas, everybody's together. The total ionic equation, we break apart anything that should be broken apart, which is really strong electrolytes. And then we find our spectator ions, and then we have our net ionic equation, which basically tells us what is going on. Any questions on that? Yeah. Not necessarily in this case. We're going to talk about solubility rules here in just a second, and a lot of spectator ions are pretty much things that are soluble in everything, which means they're not going to really mix with anything to make a solid. So there's just going to always be flying around. So it's really those things. So not necessarily the higher charge would result in that. Yeah. The whole entire thing here. So before I scribbled and all over it here, this original equation here, we basically wrote everybody in their proper formulas. Like when we were doing nomenclature, right? We put everybody together, positive, negatives, balance it out to zero. That's the molecular equation where we use all of our things. Included in the molecular equation, as you can see, are our spectator ions, right? Like our nitrate and our sodium, which ultimately is not really doing much in this reaction. So that's why we kind of do the other two equations to represent what is sort of really happening in this reaction. And that's really what's happening when you mix all those things together. Really, the nitrate and the sodium aren't doing much. So basically, when everybody goes for a swim, like into the beaker here, you know, you get a lead 2 guy floating around, you get a nitrate guys floating around, you get some sodium ions floating around, and you get some I floating around. So what happens in this particular case, it is just, you know, the lead and these two guys that are really attracted to each other, and they basically drop out. Guess I'll add one more I in there. Drop out into a solid. The rest of all these guys are just still floating around in the solution part, the liquid part of it, if you will, and the solid part which contains those two guys. So that's really what's happening as everybody kind of drops out of solution. Exactly. So really the net ionic equation is oftentimes used to illustrate exactly what's happening. So what that usually will involve is, in this case, you'll either have a net ionic equation that makes a solid, which is one reason why a reaction takes place, or you could have a net ionic equation that makes water, which again is another reason why a reaction takes place. And that's what those two guys will end up being. Yeah. Other questions? All right. So that's sort of what all this says here. I'll do my correction of a 2, should be there. So this is basically what we just went through. So let's take a look at another one here. Let's say we had silver nitrate plus some potassium chloride makes a little potassium nitrate and some silver chloride. So why don't you take a second here and write the total ionic equation? Why don't you write the net ionic equation? And why don't you ID the spectator ions here? So take a moment and see what you come up with here. Okay, let's take a look. So once again, almost a safe bet if you see an ionic compound and it's aqueous, that's going to be a strong electrolyte. Again, as long as it's not one of those kind of weak acids or something like that, or weak bases to kind of maybe squeeze in there occasionally. Probably not too much in our class, but for the most part, if it's ionic, it's going to be a strong electrolyte, which means it's going to break apart. So our silver nitrate here would break apart into a silver ion and a nitrate ion. This potassium chloride would also break apart as it's a strong electrolyte into a potassium ion and a chloride ion. To our other side, once again, we have another aqueous ionic compound here, which would break apart into a potassium and a nitrate ion. And this is a solid, which again does need to stay together. So I'll just go underneath here and to silver chloride, which would be a solid. This would be our total ionic equation. This is again what's really happening when we kind of dump those two reagents together in a beaker. From this equation, we can find our spectator ions, which in this case, their spectator ions are what things? It is nitrate, which looks the same on both sides. And it is the potassium, which looks the same on both sides. So those two right there would be our spectator ions, would be our potassium ion and our nitrate ion. Any questions on that? So, yeah. Chloride, it was a solid. So because it's a solid, the only way it can basically be a solid is those two guys got to stay together. Yeah. They do matter. So anything that's AQ is aqueous, which means it's basically like a solution. And it usually means it's soluble. So if it's an ionic compound that has the AQ symbol next to it, it pretty much will indicate that it's probably a strong electrolyte in most cases. And you can break it apart. Anything that has the even, which is like liquid, typically will stay together. Other questions? Okay, so with our total ionic equation, once again, you do need to make sure that you got charges on all these guys that are ions. So you got to make sure that those guys have the charges. We're going to cancel out our spectator ions, and that is going to leave us what is truly happening in this equation, which is our net ionic equation. And basically what is happening, it is the silver ion that's going to find the chloride ion in this case. And you will make some silver chloride, which is a solid. Once again, here, the formation of a solid, which is really the reason why this reaction is taking place. And that equation basically tells us what is happening here in this reaction. Any questions on that there? Again, for the net ionic equation, the ions, again, need to have charges. So it's a very common mistake people make when they write these equations. They don't include the charge. That's an ion, you write a formula for an ion, make sure you got the charge on it. Any questions on any of that stuff there? How do we know if we kind of put these two ions together, are we going to get a solid or we're not going to get a solid? So there are some rules that we follow to help us decide when we kind of combo these two things together, do we expect some type of solid to form? And those are solubility rules. And you might have remembered you had actually a solubility table kind of given to you in one of those earlier experiments, way too early. It was that table where it had a bunch of S's and I's in it, and like the ions, and you kind of move your fingers to a box and it said I or S in it. Those were solubility rules, which was a month early. I don't know why they put it in that experiment. But we use those rules to help us decide whether or not, we would expect a solid to sort of form. So the solubility means obviously if something is soluble in each other, if it's a solid in a liquid, the solid will dissolve in the liquid and basically mix. So if it is determined that something is soluble, it actually will get that AQ symbol next to it. So if you use these sort of solubility rules to determine that, yes, this thing is soluble, it gets the aqueous symbol. And basically what that means is no solid is forming. So you can put those guys together. They're never going to really come together and they're not going to make a solid. Basically what that means is those two ions will just be floating around the solution, basically free and stuff. Now, if you look at the solubility rules and it says that those combination there is going to be insoluble, those are the guys that will get the solid symbol next to it, which indicates that those two ions will not continue to float around. They will then be attracted to each other and will basically drop out of solution, if you want to think about it that way, and become a solid. So those two guys will come together and make a solid. I know, soluble you think would have the S symbol, but no, it doesn't. So insoluble has the solid symbol there, and that's why it is. So they are really broken up into these three sort of categories: soluble, slightly soluble, and insoluble. I will say probably not too much you're going to come across slightly soluble, but it does pop up occasionally, and it does mean what it sounds like. It is slightly soluble. So some of it will dissolve, some of it won't dissolve. Most people consider slightly soluble to be more like being insoluble in a sense. Yeah. Now, these solubility rules, I think for the most part, we'll see soluble and insoluble in most cases in this class. But again, slightly soluble does sort of pop up occasionally. When we look at solubility rules, we could use it to help us decide solid or not. Even if something is technically insoluble, right? The rules say, hey, when you put these two things together, you always get a solid. The true answer is that's not really truly the case. Even something that is technically insoluble has some degree of solubility. It's going to be super, super small, but there's some degree of it that's going to dissolve. But it's so small, it's basically considered insoluble. So even things, you'll learn more about that when you go to 1B and talk about solubility. But even things that are technically insoluble, yeah, it has some degree of some solubility to it, but it is super, super small, which is why it's considered to be a solid wood form. So let's talk about these rules here. And these are the solubility rules. What we're looking at here is for things that are soluble in water. And because these are soluble in water, that means technically speaking, everybody here, if it follows these rules, should get the aqueous symbol. So let's talk about these things here. First off, anybody in group 1 on the periodic table is going to be soluble in everything. So if you look at a chemical formula and you see a sodium, you see a potassium, you don't need to look any further. You can just lay up an AQ next to it. It's going to be soluble. There's no exceptions. So if you see any of those guys, you for sure know it will be soluble, which means you will not expect a solid to form. So there would be no solid that would form here. Anything that has ammonium, which is NH4 plus, not NH3, but NH4 plus in it, will also be soluble. There's no exception. So once again, if you're looking at the formula and you see NH4 in it, just write aqueous next to it. It is going to be soluble. You would not expect a solid to form. In addition, anybody that has nitrate, chlorate, or perchlorate in the formula are also going to be soluble. And again, there's no exceptions. So as soon as you see something with nitrate in the formula, you know that's going to be soluble. You will not get a solid at all from that thing. Now, when we get to chloride, bromides, or iodide, so that's like Cl minus, Br minus, and I minus over here. These guys are going to be soluble in everything, but there are some exceptions. So there are 3 major exceptions for chloride, bromide, and iodide. And it is these guys right here. If you have any of those guys that have silver, that is mercury 1, and that is lead 2. So any of these 3 guys happen to be hooked up with a chloride, a bromide, or an iodide, it is going to be the opposite of what normally is. So normally it is soluble. So if one of these exceptions exists, it is the opposite. And these guys would then become insoluble and you would get a solid that would form. So on these rules, there's like, these are the rules for things that are soluble, but if there's exceptions, it becomes the opposite. So it goes from being soluble to being insoluble in this case. You would get that solid that would form. Most sulfates are soluble in everything except for silver sulfate and calcium sulfate, which is slightly soluble. But the main exceptions for sulfate are what we see at the bottom there. If you have sulfate that has barium, mercury 2, or lead, they are going to be the opposite and going to be insoluble. So if you had sulfate that hooked up with any of those guys, they would be the opposite as well and become insoluble. Any questions on that there? So everybody on this list is technically soluble unless it's an exception, then the exception would make it insoluble and a solid would form. Any questions on that there? Now let's take a look at some things that are normally going to be insoluble. So these are things that normally would be a solid. So these guys are normally the guys that are going to make a precipitate and are going to be solid. Hydroxides, except for anybody in group 1, which is basically what this is, anybody in group 1 on the periodic table, which is the same rule as we saw on the previous slide, right? Anybody in group 1 is soluble. So sodium hydroxide is soluble. Yeah. Lead 2 hydroxide, insoluble, right? Because it was the opposite there. So that is what those are. Anything with carbonates, phosphates, or sulfides are going to be soluble, except the alkali metals and ammonia, which is our other slide there. These guys then would be aqueous. So something with the alkali metals would be aqueous here. So these are a few of the exceptions that we see. Anybody with group 1, once again, is going to be soluble. Anybody with group 1 and ammonia will be soluble as well. So it really is the same rules we saw on the previous slide, but that would be the exception here. So that is why when we looked at earlier our silver nitrate plus our potassium chloride, making our potassium nitrate and our silver chloride. So if we were going to use our solubility rules here to help us with this, we would look at the first one, which is silver nitrate. Although we may not be able to see silver directly on there, as soon as I see nitrate on the previous slide, it says it is soluble in everything, no exceptions, which means that guy will get the aqueous symbol. We would not expect a solid. Once I get to this guy here and I see potassium, which is group 1 on the periodic table, that's really as far as I need to go because it is soluble in everything. There is no exception, which means it would get an aqueous symbol. I could also look at the chloride, which is on the previous slide, and the chloride is soluble. Chloride is soluble in everything except for these 3 guys. And in this particular case, that is not one of the 3 guys. So that gives us the same answer that it is soluble. Once I look at potassium, it is soluble in everything. That's as far as I need to go. It will be aqueous. When I look at nitrate, it is also soluble in everything. That is as far as I need to go. It will give us our aqueous symbol. When I look at silver, I might not be able to see it, but once again, I'm going to look at chloride. And once again, I'm going to look and see chloride is soluble in everything except when it is hooked up, for example, with silver, which would be the case here. So because it is normally soluble, and this is an exception, it goes from being soluble to becoming insoluble. And that is how we know that is the guy that's going to make the solid when we put these together. Any questions on that there? So why don't you try one here? Why don't we do barium bromide plus some potassium sulfate, making a little potassium bromide, and we got there a little barium sulfate. Do a little balancing like on my chemistry class here. There we go. All right, so use solubility rules and predict our states. Then also write the total ionic equation, write the net ionic equation, and identify the spectator ions. Use our solubility rules to determine, first off, the solubility of everybody here. We won't see maybe barium there, but we do see bromide on the previous slide. And once again, bromides are soluble in everything except silver, lead, and mercury, which is not the case here, which means that this guy should get the aqueous symbol. When I come to the next one, I see potassium. Frankly, that's as far as I need to go because that is soluble in everything, which means this guy also should get the aqueous symbol. Coming to this side, once again, I see the potassium, which is soluble in everything. So that should get the aqueous symbol. And my barium sulfate here, sulfate, if we look on the previous page, is soluble in everything except barium is one of the exceptions. So because it's an exception, that would be my solid in this case. So any questions on that there? To get to our total ionic equation, that means that we could safely break apart the barium into barium with a +2 charge. We then would have 2 of the Br minuses. Again, this 2 comes to the front when we do total ionic equation. This 2 here would also come to the front for our potassium. And we would have 1 sulfate there. On the other side, this 2 would get distributed to both of those when we break it apart. And that would give us 2 potassium ions and 2 bromide ions. And this, which is our solid, would stay together. Any questions on the total ionic equation? We can see that our spectator ions in this case are here. Looks like a couple of bromines on both sides, a couple of potassiums on both sides. Those would be our spectator ions, which we would cancel out. By the way, if you balance everything correctly and you get to this part, they should completely cancel out. So if you find yourself with like 2 ions on one side and only 1 on the other side, something's not balanced correctly. So they should always properly cancel out. So those 2, which are our spectator ions, will then leave us really what's happening in this case. It is the barium ion that's going to find the sulfate ion and give us barium sulfate, which is our solid. And obviously this is our net ionic equation. That would be our total ionic equation. And this would be our molecular equation on the bottom. Yeah. Any questions on any of those things? How to use solubility rules? Anything?